Okay, so the other, now I want to define important set of equation, which is ordinary differential equations. So let's go through that and see how are they defined, and then I'm going to solve one simple example of that, and then we will move forward with our ordinary partial differential equations, which is the main part of the course. So let's see what is ordinary differential equations. So the abbreviative of this is ODE. So whenever I talk about ODEs, I mean ordinary differential equations, okay? And one example of that is this. If you define it as dx dt, where x is a vector field, you can define this. This is also equivalent to x dot because this is the first order derivative in time. We can write it as x dot, okay, of t. This equals to f x t and t, okay? So this is how this is a differential equation, ordinary differential equation, where f is from u to v space 2, which is a subset of Rn, real numbers to the power n, and R. So this is what it gets as the input, and the output of the function is a vector in nth dimension, okay? So for us, like, n is usually typically 3 because we have 3 dimension x, y, z, but I wanted to just write a general form of it depending on the different fields. So this defines a time dependent vector field on a subset U of Rn for each t in a subset V of R by allowing U to be in n-dimensional space and V to be in one-dimensional space, okay? So this will prepare us for some of the PDE methods that we are going to talk about partial differential equations. So this is like a simple definition of ordinary differential equation, and we can take the integral of this. So the integral form of ODE. So if you want to solve this ODE, you can take an integral of that and try to solve it. And the way we typically do is we bring all the same variables in one side of the equation, and the same side of the equation, the other, like the time into the other side of the equation, and then take the integral. Okay, so for example here, if we take the integral xt on the left hand side, so the integral of this is gonna be x naught plus the integral t0 to t of f xs ds. Okay, so this is, if you take the integral form of that, you can write it this way. And I'm gonna solve an example for this ODE so you get more familiar with that. Okay, so let's start an example. Okay, solve and describe the behavior of the following ODE. And the ODE that we have is dx dt, which is x dot equals to x squared. Okay. So let's solve this. So in order to solve it, we are gonna take an integral of it. So what I'm gonna do is I'm gonna take the x to this side and take t to the other side. And then I'm gonna take an integral of that. So what I'm gonna have is integral of x0 to xt dx over x squared equals to the integral of 0 to t of dt, and this is gonna give me 1 over x. The first part is gonna give me 1 over x, which is the integral of 1 over x squared from x0 to xt. The second part, the second integral, is gonna just give me t, right? So if you don't remember, this is x minus 2, and the integral of that is gonna be x minus 1, right? So this is how I wrote it here. And this is gonna give me x0 over 1 minus x0 t. Right? So this is how we can solve this equation. And now let's see what is the behavior of this. So this is the final solution of that. And let's see what is the behavior of that. So if x0 is greater than 0, xt is gonna go to positive infinity as t goes to t star, or 1 over x0. This is gonna go to infinity from below. So let's see how it looks like. Okay, so I can show it here as this. If we plot it, so a positive x0, so this is xt, and we have a positive x0, so x0 can be here, for example. And then we have 1 over x0 is where it's gonna go to infinity, right? So I'm gonna show it like here, and this is 1 over x0, which is t star. And then if you plot it, you will see something like this. And here it goes to infinity, positive infinity from below. So here the solution is gonna blown up, okay, as it goes to here. And if x0 is smaller than 0, is negative number, x t is gonna go to negative infinity as t goes to t star, or 1 x over 0 from above. So this is the difference. This time it's gonna go from above, and let's see what it looks like. So if we plot it, this time x0 is negative, and here we can say is t star, which is 1 over x0. And if you plot this, you're gonna get something like this. So it's gonna go to minus infinity this time, right? So it's gonna blown up here. Okay, so you see that this equation, this ODE, depending on the x0, if it is positive or negative. And I think in the here I had to say that x at 0 is x0. Depending on the initial condition, it can go, if you take the integral, it can either go to positive infinity at t equals to 1 over x0, or go to negative infinity. Okay, so this is the behavior of this ODE, and how can we easily solve it by just taking an integral. But of course there can be more difficult ODEs and nonlinear ODEs which need other methods for solving them. So next time I'm going to go through with this introduction of the notations. So let's go through it very quickly. So we started with some notations, and then we talked about the function continuity. We talked about order of differential equations, Taylor's theorem, which is a very important topic. We talked about this. And then we talked about the ordinary differential equations, or ODEs, the integral form of that, and just one example. Okay, and next time I'm going to gonna start talking about the partial differential equations, their classifications. So this is what we call PDEs, their classification. And after that, we are going to talk about some methods to solve them analytically. For example, method of characteristics and separation of variables. With this, I want to thank you very much and have a good week.